Hey guys, BuildZoid here, and today we're going to be taking a look at the RTX 3080 TUF PCB from ASUS. Now, before we get into this, the pictures of the PCB are from the Tech Power Up review of the RTX 3080 TUF. So thank you to Tech Power Up for providing really high-res PCB pictures in their reviews. And also, if you want information about like what temperature, operating temperatures, noise output, performance, power consumption, you should go check out their review. There will be a link to it down in the description below. And with that out of the way, let's get into it. So the RTX 3080 TUF is definitely one of the nicer RTX 3080 PCBs out there, mostly because it actually tries to be good instead of being a reference PCB downcosted basically as much as physically possible. So yeah, I rather like this card. And anyway, so as is the norm for RTX 3080s, we have the 2 rows of power stages on either side of the GPU core, and I'm now starting to wonder if my brush... No, dynamics are off. Okay. So I could have sworn this line... Oh, I have the pass... There we go. That's why it looks weird. So wondering what was going on with that. Anyway, so yeah, we have the 2 rows of power delivery on either side of the core. In terms of the actual phases that we have, the first phase over here is memory power. Then we have... Actually, this is... Yeah, okay, that is where it splits over. This is rather convenient. Like, ASUS could have totally had just a row of capacitors that doesn't end from top to bottom. But yeah, this does make distinguishing the different power rails much easier. So this is your core power. This is the MSVDD, which I like to call uncore power because it basically powers like non-core memory system stuff in the actual GPU die. I think basically the region of things it powers looks something like this. Because you have memory controllers just wrapping all around it. Actually, you also have it going up there a bit. Because you have memory controllers just wrapping the entire GPU core. And then this last phase down here is more memory power again. There. So that's our M. On the other side, we start with yet more memory power. And then we get 3 phases of core. And then 3 phases of uncore. And then 1 more phase of memory power. No, I got that mixed up. Yeah, okay, wait a minute. I think I made a mistake. Yeah, I made a mistake. Oops. No, what are you doing? Oh, we're on the wrong layer. Okay, well, that makes sense. Anyway, no, idiot. You just fixed... I literally just corrected that. It's just like, do it again. Anyway... So, yeah, no, it goes memory, core, memory, uncore on this side. So, you might be looking at this and wondering, why is the memory VRM basically everywhere on this PCB? And so the idea behind doing this is that normally if you just, like, the thing with the memory is that it's scattered all around the GPU core, so there's a very large power plane, and the GDDR6 memory chips pull kind of a lot of power. And also, like GDDR6 is already more demanding in terms of power delivery requirements, but GDDR6X takes that to like the next level. And so one of the issues with having, you know, a bunch of high power draw devices scattered around a really large power plane is that if you feed power into them from just one side, you're going to have more voltage on one end of the power plane than on the opposite, whatever is the opposite end of the power plane. So on GDDR5, like there are GDDR5 cards where you can end up seeing some, because the thing is with GDDR6 and GDDR6X cards, like the power delivery for the memory is so important that they really do their best to avoid this. But there are GDDR5 cards where you could end up with a power plane where like one end of the one side of the memory chips is getting 1.55 volts and the other side is getting 1.5 volts, which is still in spec for like GDDR5 spec is anywhere between like, well, I think there was low voltage GDDR5 as well, which might have been 1.35 volts, but you'd basically have a voltage range that goes all the way up to like 1.6 volts. So it wasn't really a big deal if you were like 50 millivolts off on your operating voltage for the memory chips. However, for GDDR6X, running some of the memory chips at 1.4 volts probably wouldn't cause any major issues, but the spec is literally 1.35 volts. So you really do want to keep all of the memory chips as close to 1.35 volts as possible. And so, you know, various ways you can work around the whole current traveling through a power plane with resistance issue is you can have a better power plane, or you can just scatter the memory VRM all around the power plane so that there's no, so that all memory chips are relatively close to some source of current, which is the memory VRM phases themselves. So this is just a power delivery optimization for the memory, which is why we have the memory phases just about everywhere. Or more like a power distribution optimization. And then we have a similar thing going on with the core and uncore power rails, where you have, some core VRM over here, then some more core VRM over here. I'm not really a fan of having the imbalanced distribution. I assume it doesn't make too much of a difference, but theoretically it would be better if you had like an even split between the VRMs, which is what you would see on like, say, an Nvidia Titan V. Where you have exactly the same amount of phases on either side of the chip. But even this is like better than because the thing is, if you look at like old GDDR5 cards that had very high power very high power requirements, what you'd usually end up with is like 2 rows of VRM, and then you ended up with a really long power plane, which again just is suboptimal for power delivery. It's not as efficient as if you like basically your goal is to get the voltage regulator as close to the thing it's powering as possible. And so by splitting the VRM across like this, you don't run into the issue of like, well, if we put 3 more phases up here, it's just going to go off the edge of the card. So it helps with sort of locating the VRM onto the PCB, and it also helps a bit with power distribution again. And we have the same thing going on with the uncore rail, which is, also on either side of the GPU. So in terms of power stage counts, we have memory power. We've got a 4-phase with 4 power stages. For core power, we've got 8 phases, but 10 power stages, which I really want to measure how this works one day. Actually, I'm going to just do power stage like that. Yeah, so 10 power stages. And then uncore, we've got a 6-phase with 6 power stages. Which that is there. So the interesting thing here is actually the phase count. Well, you have a phase count advantage compared to most reference RTX 3080s on the memory. In fact, I think you have more memory phases than even the 3080 Founders Edition. So ASUS has given you a slight upgrade there. The uncore power being a 6-phase is most cards come with 5-phase uncore power instead of 6, so that's a slight upgrade as well. And then the 8-phase V-core is actually the norm for 3080s, but you don't normally get 10 power stages on that. So there's a slight upgrade in terms of power handling capacity there by adding the extra power stages. In terms of the controllers, this card also uses the slightly better option. Like, that's kind of the thing that I really like about this card, is it just makes a bunch of slight upgrades to everything. Compared to, say, the reference cards or even the Founders Edition, which is, like, most of the reference cards are just a step down from the Founders Edition, and this in some areas really is a bit of an upgrade. So for the controllers, we've got a UP9512 right here, which I believe this one is for the V-Core. And that one's running in, so we're going to put C next to it for core, and that one should be running in full 8-phase mode. The UP9512 is a 8-phase voltage controller, which is why the 10 power stage V-Core is kind of weird, but we've seen similar things with like 2080 Ti's where you had like, it was also, I think, 10 power stages V-Core with 8-phase controllers. But there's also been cards where you'd have like 16 power stages or 13 power stages on a 8-phase rail. So, well, 16 makes sense because you just you just have 2 oversized phases. But when you have 2 phase, like with this, I would assume there's 2 phases that are significantly larger than the rest, and it's just like, how does the controller deal with that? Is one thing I've always really wondered, because it's not like this kind of VRM configuration hasn't been a thing until basically the 2080 Ti. Like, it's just never ever seen anything like that before. Because the thing is, like, I've seen cards where you'd have 2 power stages sharing an inductor, and that would just be a power balancing thing. But I've never, like, these are separate sets of components completely. So yeah, very weird, but it's not particularly new. I've just never gotten a chance to see how that works in action. In theory, it should just be a case of the controller balancing the current between the phases a little bit weird to skew it towards the oversized phases. Yeah, anyway, so we have a UP9512 for core over there, then we have another UP9512 down here. This one is for the Uncore, or at least I assume it's for the Uncore, and so this one's running in 6-phase mode. And then over here, we have a smaller UP9512, and what I think is going on with that is that internally this is still a full-size UP9512 with 8 phases. However, it's just using a reduced pin count package to reduce how much PCB space it uses. And this chip only goes up to 4 phases. And it is running in 4-phase mode. Like internally, it might go up to 8 phases, but there's not enough pins to actually connect 8 phases, all 8 phases on that one. So anyway, UP9512 is not the cheapest controller that you can use to build a 3080, which is why I also consider this a slight upgrade. It goes, let's do this on the core one because that's the most useful one. So it goes up to 1.2 megahertz switching frequency, which is basically twice as much as what you'd get out of a UP9511, which is the cheapest controller that you could get. Though it is worth noting you probably shouldn't be running anywhere near 1 megahertz switching frequency because at that point, well, it's interesting. Some power stages will straight up refuse to function once you get into frequencies that high, and a lot of power stages will just kind of get really, really inefficient. So you probably would you wouldn't want to the large frequency range isn't really that useful. But there's no harm in being able to go from like 300 kilohertz to maybe 800 kilohertz. 300 kilohertz is normally the stock switching frequency for a VRM, though it could be slightly higher, all the way up to like 500 kilohertz. I'm without the card in hand, I can't be certain about what it's configured to. Anyway, so up to 1.2 megahertz switching frequency, and it does come with an I2C interface, which ASUS has conveniently given you a header for right there. So you can get voltage control, switching frequency control, and a limited amount of load line calibration settings by basically, communicating with the chip over the I2C interface. There is I believe the data sheet for the UP9512 at this point is public. That data sheet's been kind of weird because it popped up around the RTX 2080 Ti launch. Then I think it disappeared, and I found it again while working on the 3080. So I think UPI Semiconductor has put that data sheet back up. And now it's public, and there's actually a full register map, which is really cool. But if you're lazy, what you could do instead is you could get an Elmore Labs EVC voltage controller, and basically just hook that up to the card, and the EVC already has full support. Well, I'm not sure if it's full support, but it already supports a lot of the functionality of the UP9512, and I'm sure if you ask Elmore for more functionality, he'd be more than happy to add it. Though, as long as you have basically load line calibration, switching frequency, and voltage control, that's basically everything you need. And maybe you might also want to have like a overcurrent protection disable, which I would assume is also just supported on the EVC2 with a UP9512 just out of the box. So yeah, that's really cool about this card is just it makes it really easy to get full volt. Well, if you have an Elmore EVC2, it's really easy to get voltage control on this card. Unfortunately, that will not fix the and you'll get control of all of the controllers because the I2C interface is shared between all of them. So yeah, you basically hook up the EVC2 and you get memory voltage control, core voltage control, and uncore voltage control. So that's pretty cool. If you want to do extreme overclocking with the card, though, there are better PCBs for that, just more powerful power delivery, better capacitor selection, which, you'd be looking at a Strix for that. Very specifically a Strix for that. I've so far not seen a card that beats the Strix in terms of PCB build quality. And if you're wondering if I'll do a PCB breakdown of the Strix, I will. You should subscribe so that you don't miss it. I'm not sure when it'll be uploaded, though. Anyway, so yeah, ASUS is not using the bare minimum in terms of voltage controllers here, so that's nice. In terms of the power stages, they've also done a slight upgrade. That's I've mentioned it earlier, that's the thing with this card, is slight upgrades absolutely everywhere. So the power stages that they're using are SiC 641s, and these are 641As, I believe. It says 641 in my notes, so I'm going to assume these are actually 641s, and the person writing my notes wasn't an idiot. That being me, that's a big assumption to make right there. Anyway, these are 55 amp DRMOS components, which is another, like, not only do we have more, power stages than what you normally get, you get 10% more powerful power stages than what you normally get, which actually doesn't really make much of a difference. Like, the difference between a 50 amp and a 55 amp power stage is basically nothing. But what's interesting about these is that they have a very, like, the feature set of that these have is kind of interesting because they have the usual thermal flag system for just alerting the voltage controller, hey, I'm overheating, but they don't have temperature monitoring, which is pretty normal. They have overcurrent protection, which is kind of like built in to the actual power stage. You have overcurrent protection, which is very weird considering that they don't have current monitoring functionality. So the controller can't just ask the chips for the output current, which is just kind of like if you have overcurrent protection, that chip is capable of measuring the current flowing through it somehow. So why there isn't a way to monitor that directly, I am not entirely sure. Because these aren't smart power stages. Like when I read the safety feature specs of these chips, I was like, whoa, that looks like a smart power stage. And then I combed through the data sheet, and it's just and compared other data sheets from Vishay Semiconductor for if these are smart power stages, and it's like, nope, no, these aren't. But they have most of the feature set. So yeah, you have OCP, you also have over temperature protection built in, as well as the thermal flag system, and high side MOSFET short circuit protection, which is really cool. In theory, if the VRM explodes, there's much less chance that it'll destroy your GPU core. So yeah, these are really cool. Though in terms of what they do to efficiency, it really doesn't make that much of a difference, though it's still higher than what you get on most 3080s because you just have more of the power stages. So let's talk power delivery capabilities. Outputting 1.05 volts, and unfortunately the performance metrics for these chips are not in the public datasheet for them, or it's not really a datasheet, it's like a I think it's called a data brief when it's 3 pages and doesn't include any details, or I think it's 6 pages. The point is, it's not a complete datasheet and there's no performance curves. But anyway, at 1.05, so I'm using the performance of an SIC 652, which I believe is either a 50 amp DRMOS or a 55 amp DRMOS. I can't remember. But if you Google it, I'm sure it'll point you to the Vishay Semiconductor website and tell you if I'm using the 50 amp part or not. The thing is, between 50 amps and 55 amps, there's not that much of a difference. Anyway, 1.05 volts output voltage and 300 kilohertz switching frequency. We're going to be looking at the following kinds of heat loss on the in the VRM. So 200 amps output current, you're going to see about 17 watts of heat dissipation, which is really not bad. That's actually really good efficiency. Then putting out 250 amps, we're going to be getting about 27 watts of heat output, which is still better than what you get on the vast majority of 3080s. And again, not bad because, you have, all of that heat is shared across all of the power stages here. So it shouldn't be very hard to, cool that with just, strong airflow. And then when you get up to 300 amps output, it starts producing about 37 watts of heat, which, again, really isn't, depending on the cooling system, that is definitely, not difficult to deal with, depending on how you're cooling the VRM. So, yeah, the efficiency is good enough. And again, it's just a slight upgrade. Unfortunately, even though I'm not using the datasheet for the SIC 641, the SIC 652 doesn't go past the 30 amp. It's a 50 amp power stage, but the performance curves only go up to 30 amps. And the thing is, the reason why the power stages do that is that you're really not supposed to be using them at their peak rated output current. Even if it's peak sustained output current, it's you're still not supposed to be using them like that because you need just such an insane amount of cooling at that point. Most 50 amp power stages at 50 amps output will be spitting out 10 watts of heat each. At which point it's just you need one hell of a heatsink for your VRM, because something like this, 10 power stage V-core here would be spitting out 100 watts, and it's just well, good luck with that. Good luck with dealing with that. So the documentation generally doesn't go all the way up, though 30 amps is really low as a cutoff for the performance curve, which is kind of annoying. But still, within the lower current ranges, these actually perform about as well as any other 50 amp or 50 amp DRMOS components out there, if not slightly better. So yeah, in terms of power delivery, ASUS, in terms of current handling capacity, ASUS has done a slight upgrade to the VRM here. And I can't remember if this is actually slightly better or about the same as the Founders Edition. Because the thing is, the Founders Edition definitely has less power stages, but the Nvidia decided to go with like 70 amp smart power stages, which, well, the difference between like a 50 and a 60 isn't much, but the difference between a 50 and a 70 is kind of a lot. So yeah, I can't, like, I should have probably included in my notes, but there's a PCB breakdown on Gamers Nexus of the Founders Edition, so if you want to know the heat dissipation for that VRM, you can go check that video out. Anyway, let's talk about the Encore power delivery. So the Encore is a 6-phase, as I mentioned before, and so it doesn't need to deliver as much current, and it also can't because there's just less power stages in it. Same operating parameters, 1.05 volts, 300 kilohertz switching frequency. We are going to be looking at 120 amps output producing about, 120 amps output, about 11 watts of heat. 180 amps output is going to be producing about 22 watts of heat. So, yeah, this is going to be a bit warm, but I really don't know how much power the Encore rail is supposed to, like, output, because I've not had a chance to measure one of these cards in action, unfortunately. Mostly because, like, good luck buying a 3080, right? Anyway, let's talk memory power delivery. So memory, 4-phase, and the thing is, ASUS is using these SIC641A power stages absolutely everywhere. So basically every single VRM on this card has a slight power delivery upgrade. So memory power, we're looking at 1.35 volts because I did actually scale the efficient heat outputs to higher voltages for this time. Remembered to do that. 300 kilohertz switching frequency. We got 40 amps output, producing about 4 watts of heat. 60 amps output, producing about 7 watts of heat, which I believe is slightly more. Like, the thing is, there's supposed to be like a decimal point, but I think, like, I don't really think that makes too much sense to include that much, like, detail in heat dissipation figures for a VRM like this. So yeah, anyway, 7 watts is really not much spread across 4 different power stages, and 80 amps output, you're going to be looking at about 9 watts, which still well, the thing is that, like, that's the thing, is like the memory VRM here is probably going to be more, like, its operating temperature is going to be much more dependent on the operating temperature of, like, the core and uncore VRMs than it is going to be on its own heat output, right? Because compared to the 17 to 40 watts of heat output that the core, or 11 to 22 watts of heat output of the uncore VRM, like, the memory VRM is basically nothing. So it really, and also I'm not sure, like, I don't think you'd ever, well, maybe if you overvolted the GDDR6X, it might start pulling 80 amps at some point. But I believe at stock it should be somewhere between 40 and 60. So there you've got really, like, the memory VRM is not going to have any issues. And even at 80 amps output, like, you're still not going to have issues, right? Like, that's just 20 amps coming out of 55 amp power stages. So yeah, really the memory VRM on this card is kind of overkill. So that's the power delivery, and just in general, ASUS has made slight upgrades to it everywhere. You get, more current handling capacity, more phases, better power stages, better voltage controllers than the bare minimum for a 3080. So that's nice. And then on the back of the card, for the actual output, like the capacitor configuration of this card, I'm a huge fan of it because we've just got SMD polymer capacitors, and these are all from APAC, which is not as these aren't as good as, like, your Panasonic SMD aluminum polymer capacitors, and these are aluminum polymers from APAC. But the thing is, they're still SMD polymer capacitors, which just gives them a huge ESL advantage compared to through-hole polymer capacitors, which basically means these are far better at power filtering than your standard through-hole capacitors. The downside is they're also way more expensive, even if they're made by APAC, which is considered, like, the cheap option for sort of high-end capacitors, because there's much worse you could go for as well. But yeah, it's still, like, and that's the thing, is, like, ASUS is just making slight upgrades. So if you look at, like, the Strix is on actual SP caps from Panasonic, which are better than these APAC aluminum polymers. But the thing is, they're also probably, like, twice as expensive, if not more. So that's the reason that, like, we're seeing these APAC capacitors, because well, it's a TUF card. It's not supposed to be the most expensive card in the lineup. But yeah, these should give you a slight edge in terms of overclocking capabilities. And then, of course, we have the very controversial capacitors right behind the core, which not much of a controversy with what ASUS has done here because we just have a bunch of multi-layer ceramics instead of the usual configuration, including two SMD polymer capacitors, right? Which you'd normally have like two SMD polymers up here and then two more down here. And I believe these are all uncore and these are all core, though I'm not entirely certain about that split. Anyway, the thing with the multi-layer ceramics is that they so similar to how the SMD polymers have an ESL advantage over your through-hole polymers, the multi-layer ceramics have another advantage in terms of ESL over the SMD polymers because they're even smaller. The downside to them is well, they're again just more expensive per microfarad. So if there's a minimum amount of capacitance that you need, it's going to cost more to reach it. But yeah, ASUS is certainly not cutting any corners by having this capacitor configuration here. I'm kind of like the color of these being very bright yellow makes me, well, the thing is that bright yellow ceramic material generally indicates like a higher than standard capacitance for multi-layer ceramics, at least in my experience, because I have like a R929, like I had an R9290X, which died and then I used it for spare parts, and well, it had a bunch of really yellow multi-layer ceramics behind the core, and to my surprise, they were 47 microfarads, which is about as high as you can get in the 0805 capacitor package without going for some like low temp, like not that high temperature endurance rated capacitors. So, yeah, that's the like at the same time these could still be 22s. They're almost certainly not 10 microfarads because the Nvidia minimum specification requires like 220 microfarads of capacitance per like SMD capacitor position. But yeah, that's the thing is just like these could be 22s, they could also be 33s or even 40. Like 33s are a weird value, but 47s would definitely, like if ASUS used 47s here, it wouldn't surprise me. 22s would though be far more sensible for a card that's in the TUF lineup. So yeah, compared to basically all the the thing is this is maybe a slightly better capacitor configuration than what you'd get even on the Founders Edition. Though interestingly enough, the Founders Edition actually uses more expensive voltage controllers in the form of the monolithics. Well, just watch the Founders Edition PCB Breakdown for that. So yeah, I'm a big fan of what ASUS has done here with the capacitors. We've got all SMD aluminum polymers for the bulk capacitance, and then right behind the core we have a bunch of multi-layer ceramics, which is definitely the best way in terms of like having maximum overclocking headroom. So then, though when I say maximum overclocking headroom, the difference between having like, well, I'm not sure. Like the thing is, I've not measured it, but in the past, I think the most I've ever had as a difference between like with different capacitor configurations on cards was like 40-ish megahertz. Which admittedly on the 20 series, or like that was on cards that run in like the gigahertz range. The 30 series runs in the 2 gigahertz range. So, you might see a bigger difference, but it also depends like how bad just how bad the card you're comparing against is. But certainly on average, I would expect the TUF cards to clock a little bit higher than most other 3080s. And when I say a little bit higher, we're probably talking like 20 megahertz. So, which 20 megahertz, if you're going for like world records, kind of a big deal. If you're just playing games, not a big deal at all, right? So that's kind of something to keep in mind. But yeah, this is definitely the more expensive and, in my opinion, better way of doing the power filtering for, well, a GPU. It's just like, yeah. So now, other interesting thing about this card is ASUS have also labeled a bunch of different voltage read points scattered around the card. So we have like memory power over there, though you can measure, like these aren't the only places you can measure each of those voltages. Like you can measure those voltages just off of the tabs of the capacitors. But yeah, this is far like safer and more convenient than trying to figure out which side of the capacitor you need to stab and, like which cap to stab while the card is running. And well, honestly, I would probably be measuring off of somewhere like here, but it's nice enough that they give you a easy to find voltage read point. So you have like GPU core right there, MSVDD/uncore. Then we've got memory I've already pointed out. We've got 3.3 volts. Ground is really silly because technically speaking, every screw hole on the card is ground. The I/O plate is ground. There's so many ground points that I'm not sure why they bothered to label that one of all things. But hey, if you can't find a ground, there's a ground right there. You've got 12 volts, and there's multiple 12-volt power planes because you have one for like the PCIe slot, then two for the two 8 pins. So you have 12 volts 2, 12 volts. There should be a 12 volts 1 somewhere. I don't really care about it that much, but oh well, there's a 12 volts over there. Where's the 12 volt? There should be 3 of them. I only see 2. Well, anyway. Yeah, there's a 1.8 volt rail, which is for like the BIOS chips on Nvidia cards. There's also technically a 1.8 volt rail for the actual memory chips, which might be shared with the BIOS chip 1.8 volt rail. And then we have 5 volts labeled over here. So yeah, that's a pretty cool feature if you just want to take some measurements. Makes your life a little bit easier. Other than that, we've also got a dual BIOS switch. So if you want to experiment with flashing like BIOSes that you shouldn't be running on your card, you can. I would be very surprised if like the Strix BIOS didn't work on the TUF. And well, with a BIOS switch, there's much less risk involved in, flashing a BIOS that isn't necessarily supported on your card. So yeah, that's always a really nice feature to have right there. We've got LEDs to indicate if the power connectors are plugged in. And that's kind of everything I want to cover on the back of the card. I mean, we also have more SMD capacitors on the front, but at this point you can recognize those. Also, I know they're APAC because of this logo right here. If you're wondering how to like who that manufacturer is, that's APAC. Anyway, for the current monitoring, this is a 30 series card, so we've got way more shunts than is reasonable. So we've got one there, one there, one here, one here. Like, you've got, what is that? 5? Yeah, 5 of them over here. There should be one more over there. Like, these cards have, I think, 8 normally in total. I'm not sure if this card also has 8. Anyway, there's a lot of shunts on these. And all of those shunt resistors are being monitored by this, and there should be another chip on the back. So this chip right here, what's interesting about the TUF to me is that most of the other cards use a US 5650 from UPI Semiconductor for shunt monitoring, but for whatever reason, ASUS is using the On Semiconductor 45491 chip. And basically that, like, the thing is, this chip isn't very, well, that's the chip that does all of the current monitoring. And the thing is, I've forgotten most of the data sheet at this point, but the data sheet for that is public, whereas for the US 5650, it isn't. So if you wanted to do a, fake voltage shunt mod, where instead of, because normally the way people mod the shunts is like they solder another resistor on top, and that just skews the power reading. It doesn't eliminate the power reading. And the problem with that is potentially you could still end up eventually hitting a power limit depending on just how much you skewed it, and there's probably a safety mode at some point, which, if you lower the shunt resistance too much, you might run into the safety mode, and then you're kind of screwed. But if you don't want to deal with all of that, if you want to, the thing is, technically, faking the voltage readings is far more involved than shorting out the shunts. But if you want to completely disable the card's ability to measure how much power is going into it, instead of just slightly messing up the measurement, I mean completely destroy the measurement, you can look up the datasheet for the 45491 and then just fake all of the different voltage readings that it's supposed to be getting from the different shunt resistors. And there should be another 45491 right here. I think that's another 45491. I'm not 100% certain because I can't read the label in this picture, but that should be another 45491 because the 45491 only has 3 or 4 inputs. I'm pretty sure it's 4. And since it only has 4 inputs and there's 5 shunts, well, logically there has to be another, actually there's 6 shunts, there has to be another 45491. Is there really only 6 shunts? That's kind of low for a 3080. I might have not noticed some, but yeah, there's at least 6 shunts. There might be more hiding around the card. So yeah, that's the RTX 3080 TUF from ASUS. I really like this card. Ignoring that the Strix exists, I really like this. You've got more current handling capacity than what you'd get on a reference card, maybe also more than a Founders Edition. I just can't remember right now. You've got better memory power delivery than what you get on basically the vast majority of 3080s. You've got better uncore power delivery than what you get on. I think the Founders Edition has better uncore power delivery. But then you also have the SMD bulk capacitors, which means better power filtering on the output. Then you also have all of the multi-layer ceramics. Like behind the core, you only have multi-layer ceramics, so another slight edge in terms of overclocking there. You've got the semi-digital voltage controllers so that you can actually hook up an Elmore EVC. Actually, I'm not sure if they're semi or fully digital, but I think they're partially digital. I don't think they're full digital. Anyway, you can hook up an Elmore EVC to this, get voltage control through that without having to resort to like actual like hard mod, well, complicated hard mods. It's still a mod. It's just not as difficult because like ASUS gave you the freaking connector. Like you literally just need to solder a header to that and you're basically done. Oh, and I think you might have to short the I2C interface because normally it's like read protected by Nvidia or write protected. It's write protected, yeah. Because if you could, like, there's no, like, who cares about read protection? Like, the main thing is that you can't write to the registers. So it's a little bit more involved than just soldering that connector, but it's basically just soldering that connector and then connecting an EVC2 for voltage controls. You've got dual BIOS, which is really nice to have if you're going to mess around with like flashing different BIOSes. Like, yeah, I really like this card. This is a, like, as far as RTX 3080s go, if you're not going to go for the Strix, the thing, like, I do actually have pictures for the 3080 FTW3, so you should go check out that PCB breakdown. I've not written up the notes for it, so I've not made up my mind about it yet. But I think for daily usage, this is probably one of the better, like this is definitely one of the better 3080s. I'm not sure if I'd rank it above or on par with the FTW3 just yet. And then there's the Strix, which is, a step above this. So yeah, that's the 3080 TUF. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both of those help out immensely with running the channel. And so it would be much appreciated if you'd check those links out. And that's it for the video. So thanks for watching and goodbye.